years of experience. He has strong interest in high performance computing, computer networks, network security, computer architecture, and operating systems. Anandan sir has worked on a variety of projects related to high performance computing, including the design, implementation, and maintenance of high performance computing clusters and tier 2 data centers. He has maintained large HPC clusters at JNC ACR Bangalore and NICER Bhubaneswar. In addition to his technical skills, he has a strong academic background in computer science and engineering. He has a BTech in information technology and an MTech in network engineering, as well as a postgraduate diploma in system software design from CDAC Bangalore. Uh, Over to you, sir. Your screen is visible.
Okay. Yeah, thank you. Yeah. So good afternoon to all. Yeah. So today we will see what is the HPC and why we need HPC, science behind the calculations, everything we will see, and how to integrate GPU for HPC and how to use GPU for quantum simulation. And in future, if QPU comes, how to integrate it with HPC. Okay. So today objective for this lecture is first we have to introduce HPC to the users, participants. So what is high performance computing and how it is used to accelerate the scientific discovery. The second will be how GPU is integrated into HPC. Because earlier GPU is only graphical processor unit, so it will be used only for graphics application. Now we are using it for computation also. General purpose graphical processing unit, GPU. Third will be how to integrate this QPU, quantum processing unit, into HPC through the platform called CUDA-Q by NVIDIA. Okay. Okay. So what is research? Research has actually these four paradigms. First, we have to observe something, and from observation, we have to create a hypothesis, and we have to start the experiment. So initially, computation was not there, only three legs: observation, hypothesis, and experiment. But if you keep on doing this, if we are not getting the desired result for an experiment, so you have to do again. That means too much prototyping is needed. So too much time waste, too much money waste. So they introduced the fourth paradigm that is called computation. So that observation, hypothesis, computation, again it will be repeated once they get the near result. Then they will start the experiment so that they will avoid the prototype. Okay. That's why CMAC in Bangalore, Center for Mathematical Modeling and Simulation, they named it as a fourth paradigm institute, CSIR lab. Okay. So these are all the important scientists in the field of computation science. Okay. So first is Alan Turing. So he introduced the concept of theoretical computer through Turing machine. Then von Neumann. So still we are using von Neumann architecture. So practical implementation of the theoretical computer. Then Krylov. So he's a mathematician. He's a naval engineer in Russian army. Russian naval engineer. So he introduced the concept of numerical methods. So that with the use of numerical methods, we can simulate. So physical system can be mapped into numerical methods. So he introduced that concept. Then for numerical methods, if you want accuracy, so too much computation is needed. So most of the numerical methods now we are using is approximation technique that was introduced by Mr. Boris. Okay, he's also a Russian mathematician. So first we have to understand the physical system. Then the physical system actually mapped to the conservative law, like heat equation, those equations will be mapped to mathematical equations. Then for your particular problem, you have to constitute relationship, that is also partial differential equation. Combining conservative law and constitute relation, you are forming partial differential equation. So that equation you have to solve with computer. Okay. But partial differential equation cannot be solved by digital computer, because partial differential equation cannot be solved by digital, but it can be solved by analog computers. So in digital computer, we are converting that partial differential equation into set of linear algebraic equation. Then this linear algebraic equation is converted into matrix form, and then it is solved using computer. So this is the process. For every physical system, you have to devise the conservative law and constitute relation. Then you form the partial differential equation. Then the partial differential equation, you have to give the boundary conditions, initial condition and the final conditions. Then that has to be converted into a set of algebraic equations. Then that algebraic equation has to be mapped to matrix. Then it should be solved by computer. So what is computing? So computing is a process of manipulating data using defined algorithm. Okay, so you are manipulating the data with some algorithm. So it is a combination of physical and hardware and software. Okay, so hardware is either it can be CPU or GPU or FPGA or QPU, anything. Okay, so hardware, then software is algorithm. So you are manipulating the data. So first you are initializing the data, then you are manipulating the data, then you are getting the result. Okay, if you do the computation with CPU, then it is called CPU based computation. If you do the computation with GPU, it is called GPU based computation. Okay, what is flops? So flops is floating point operations per second. Okay, floating point operations per second. Why it is crucial in HPC? Because we should not round off. Signs need accuracy. Okay, so 1.5 should be taken as 1.5 only. It should not be rounded off to 1 or 2. Even similarly, 1.5.599999 means you have to take all the precisions. Okay, so it needs precision and range. So you need floating point operations. So precision, accuracy is needed, and range. To represent the smallest number, you have to represent it with the floating point only, not integer. For biggest number also, you have to represent with floating point number. So basically, we need floating point numbers to represent the scientific quantities, temperature, pressure, whatever it is. So we need floating point numbers for their representation. And when you are representing the numbers in terms of floating point number, your calculation also should take care of in terms of floating points only. So floating point operations per second, how much floating point operations per second you can do, that determines the power of HPC, high performance computer. Okay, so there is a website I will show you then after next two slides. Top500.org and Linpack benchmarks. Okay, they determine how much flops you can do. So 10 power 12 flops means it's a teraflop. 10 power 15 is petaflop, exaflop, like that it goes on. Okay. Okay, so floating point arithmetics. In floating point arithmetics, there are four types actually. Three types is recognized by IEEE 754. The fourth one is still in process. That is double precision, single precision, half precision, and quarter precision. Double precision means each floating point will be represented in terms of 64 bits. Half single precision means it will be represented in 32 bits. Half precision means it will be represented as 16 bits. Quarter means it will be represented as 8 bits. Okay. So usually all the scientific application, they require double precision. But for machine learning and other things, even half precision or single precision is good enough. So what is floating point operations calculations? Okay. So this is the formula. Number of cores into clock speed into instructions per cycle for floating point. Okay. For Intel, it is 32. Instruction per clock cycle for floating point, it is 32. So clock speed, your processor clock speed, either it can be 2.5 gigahertz or 3 gigahertz or 3.4 gigahertz, whatever it is, and the number of cores. If you just multiply this, because clock speed will be in the terms of gigaflops. So the answer you will get in the clock speed is in the gigahertz. So you will be getting answer in the terms of gigaflop. Then if you multiply or divide, then you will get in teraflop or exaflop. Okay. So for GPU, the number of cores is more, and the hertz is less actually compared to CPU. The clock speed of the GPU is less compared to that, and the number of floating point operations per second, that is also less when compared to CPU. But since the number of cores is more, the total number of flops will be high in terms of GPU compared to CPU. Okay, just I will show you some websites. This is the website called top500.org. Actually, this website lists all the top HPCs in the world. So November, every 6 months they will release. June and November. November we will take. So this is the list of top supercomputer India list. Sorry, not India. It's a global list. So here they mentioned this is petaflops. Rmax, Rpeak, both are there. So Rpeak is just it's a theoretical calculation, like what we did earlier. Number of cores into clock speed into instructions per cycle, floating point number. Okay, so with this calculation they are getting this number, this much petaflop. But this number is actually, there is a benchmark program called HPL, high performance linpack benchmark. Linpack is nothing but linear algebra package. So by running that, you are getting this much. That means practical. So R peak is the theoretical, R max is the practical. So this is a global list. And right now, this EL Captain HP Cray machine is the top in world. Okay. Frontier, and in India, I think we have, which is in 91st. In India, we have one machine from CDAC, I think. It's not in first 100. Yeah. So India, the first machine is in 136th position. So our theoretical teraflop, petaflop is 13.17 petaflop, and after benchmark it is 8.5. This is a practical value. This is a theoretical value. This value is calculated with the use of this formula only. Number of cores into clock speed into instructions per cycle for floating point numbers. Okay. So fundamentally, why we need computer for scientists? Why computer is needed for scientists? Actually, every physical problem into mapped into mathematical problem, and that mathematical problem has to be solved. Okay. So we need computer to solve this mathematical problem, and most of the problems belongs to partial differential equation. Partial differential equation as such, it cannot be solved by digital computer. So it has to be converted into linear algebraic equations. Then that linear algebraic equation should be mapped to matrix. Then matrix should be solved by computer. So these are all some of the mathematics used for computation. Linear equation, numeric integration and differentiation, solving partial differential equation, trigonometric, statistical analysis. So all these intrinsically requires floating point operations. Okay. So all these things require floating point operation because you cannot do with integer. Then accuracy is not achieved. So why HPC? Okay. With the normal computer, we cannot do most of the operations. We do not have single computer with that capacity. So we want to club set of computers to solve the problem. When we are when we are connecting multiple computers to solve the problem has to be parallel. So we have to make the parallel program. And for example, if you want to solve a big problem, that has to be converted into different chunks of problem, and each chunks can be given to each server, and it can be completed, and the result has to be merged. Okay, so more data volume, even single storage cannot be possible, so we use parallel file system here. Extreme complexity, so trillions of calculation has to be done, and that too in the floating point operations per second. It can be double precision, even it will be high then. So strict time constraint. For example, if you want to do weather forecasting, if you do with normal computer, you will get result after 1 month. Then 1 week's weather prediction you will get after 1 month. So there is no use. So you should have HPC to solve quickly, and then only the result will be useful. A high parallelism need. So because the problem is divided into different chunks and each part is given to different server, and then result is collected. So parallelism is needed, and huge memory and hardware demand. So everything is, these are the needs for HPC. Otherwise we can do all the operation with single servers itself. Okay, then Flynn's taxonomy. So these are all the four categories of Flynn's taxonomy. Single instruction, single data, multiple single instruction, multiple data, multiple instruction, single data, multiple instruction, multiple data. So single instruction, single data is the traditional single core CPU, Intel Pentium, these things. And single instruction, multiple data, this is a vector, it's a GPU. Multiple instruction single data, it's very rare, it is not available. But MIMD, multiple instruction multiple data, this is HPC, okay, high performance computer. So in these two types are there. In MIMD there is two types. One is shared memory and distributed memory. Shared memory architecture, and the second one is distributed memory architecture. So shared memory and distributed memory architecture. So if it is tightly coupled, that is called shared memory. That means, for example, I will show in the demo our HPC. If each core shares some, all the cores shares a memory. Okay, for example, if one server has 64 core, but that memory in the server will be some 128 GB or 512 GB, so that all the cores shares a memory. Okay, that is single node. Okay, but if you are connecting one node with another node with some special switch, then that is called distributed memory architecture. So each has different programming things. So usually HPC combined both, okay, shared memory and distributed memory. Okay, there are four laws in HPC. I think everybody knows what is Moore's law, most of the, then Amdahl's law, Gustafson law, and Dennard scaling. Okay, So Moore's law, I think many people know. So he is an Intel scientist. He predicted that for every 18 months, the number of transistors in the chip will get doubled. Okay. The number of transistors on an integrated circuit doubles approximately every 2 years, leading to an exponential increase in computational power and a decrease in relevant cost. So if you are buying a laptop, okay, now, and you are having some 1 crore transistors. If you buy laptop after 18 months, you'll be having 2 crore transistor, but the price is same. That was the Moore's law. Okay, but now it is Moore's law has been broken now, because now we are reaching nanometer level. So 2 nanometer level processor. So Moore's law is no more valid now. The second is Amdahl's law. So Amdahl's law actually gives the speed up. So for example, you have a program which is a serial code. When you do parallelizing it, you cannot parallelize 100%. Some part of the code you are parallelizing and some part you are leaving it as serial. Okay. So what is the percentage of serial code? That only determines your speed up. That is what Amdahl's law states. Okay. So this is the formula: 1 by 1 minus p plus p by n, and p is the parallel portion in the code and 1 minus p is the serial portion in the code. Okay, and p by n is the number of cores you are going to use to solve the problem. So irrespective of the number of cores, the amount of serial code will determine your speed up. Yeah. When is the quantum computer classified as the HPC? Okay, so see, we have to solve scientific problems. Now we are using HPC to solve those scientific problems. But since the problem is exponentially scaling, so our HPC cannot scale exponentially. The power requirement, cooling requirement, everything is beyond our control now. So through HPC, because the processor size, transistor size now becoming 2 nanometer also, so we cannot reduce the transistor size further, so we have to change something. So earlier HPC was done by CPU. Now we are doing HPC with GPU. In future we may need QPU for high performance computing. Basically it is computing. Whether we are using CPU, GPU or QPU, that does not matter. Okay, so then between high precision lower cores and higher parallelism lower precision, what is more important on the modern computing purpose? Higher parallelism, lower precision, what is more important for the modern computations? Yeah. So yeah, GPU cores are actually not high precision, but it is highly parallel. CPU cores are actually very strong, and it is high precision, but parallelism is less. Okay, but we need for machine learning kind of things with lower precision you can do. But for scientific computation, okay, like Gaussian, Gromax, those scientific material design softwares, still they need a higher precision. That is double precision, 64-bit. So it depends on the application. Okay, you need a higher precision or lower precision. That depends on the application. Mostly this machine learning things does not require higher precision, but this HPC computation things requires high precision. Okay, parallelism. Okay, so parallelism is actually we have a code. Okay, we have a code of, for example, say 10,000 lines. Okay, so in that some part, for example, you have loop. Okay, you are doing some program with loop 0 to 1000 or 1 lakh. So if you use the serial code 0 to 1 lakh, that loop, okay, that's the same code. Okay, same code is executing the different data or same data. Okay, so you are using the single core. Okay, single core means the time will increase, but you can divide the loop. For example, if it is 0 to 1 lakh, you can divide 0 to 10,000 to one core, 10,001 to 20,000. That operation will be carried out by another core. 2 lakh 1 to 3 lakh, so 3 lakh to 4 lakh, so like that. So you are getting the work simultaneously. Okay, simultaneously one program is executed by multiple cores simultaneously, different parts. Then there will be a barrier. Okay, because if 0 to 1 lakh is completed, then it should not give the result. For example, I want to add 1 to 100 in for loop. Okay, so I can use 10 threads. So first thread will calculate 1 to 10. Okay, second thread will calculate 11 to 20. Third thread will calculate 21 to 30. Fourth thread will calculate, so similarly it will go up to 100. Okay, then every thread will give an intermediate result. Then I am getting 10 results. Then I will use the 11th thread to multiply, so add this 10 numbers. Okay, then I will get the answer, so that the speed up will increase. That's why we need parallelism. That is called parallelism. I think it makes sense. Yeah. Okay. So yeah, we will continue slides. So that speed up, it's, for example, if we are using one core, if it takes 1 hour, it does not mean that if you use 10 core it will take only 10 minutes. There is no linear scaling. Okay, so it depends on your code. In your code, how much part of the program is parallel. For example, if your code does not have that parallel part, then you will not get that speed up. For example, some part of the code, for logic, it should be executed in serial only, it cannot be parallelized. Okay, so that part of the program, that is called serial part of the program, how much part it is. For example, that p is, Amdahl's law states that if p is the portion of the program that can be made parallel, and 1 minus p is the portion that cannot be parallelized, remain serial, then the maximum speed up that can be achieved by using n processor is given by 1 by 1 minus p plus p by n. So this is the formula to get the speed up. Okay, speed up depends on the serial portion of the code. Okay, for argument's sake, if we take, okay, my entire thing is parallel, or I will take infinite number of cores. Okay, infinite number of processor for the task. So infinite processor I am taking, but speed up will not be infinite. If I take infinite, my formula will become one by 1 minus p plus infinite by n. So infinite is 1 by 0, anything by 0 is infinity. Okay, sorry, okay, p is, okay, it is so this component will become 0. Okay, p by n, if n is infinity, p by n will become 0. P by n is infinity, that is 1 by 0. Then if you just go, it will become 0. Okay, p into 0 by 1, so anything by 0 is 0. So this component will be removed. If the number of processor is infinity, this component will remove. Okay, so that's what they mentioned. It's, if speed up n is infinity, then it become 1 by 1 minus p. Okay, so if 100% of the task is parallelized, p is equal to 1. Okay, the speed up scale limit is n. Okay, but in real scenario, the serial portion 1 minus p bottleneck performance. In real scenario, 100% parallel is not possible. Some part of the code has to be executed in serial also. Okay, so here one more example is given. Now we are considering this also. If 80% of the program can be parallelized, p is equal to 0.8 and uses 4 processors. So now n equal to 4. Okay, here n equal to 4, p equal to 0.8. Okay, and 1 minus p is 0.2. Okay, so speed up formula become 1 by 1 minus p plus p by n. Okay, so it become 2.5. So the program runs 2.5 times faster. If 80% of the code, if 80% of your program is parallel and 20% is serial, then you will get 2.5 times faster. So this is what Amdahl's law states. Okay, so here the problem size is fixed and the number of cores they are increasing. Okay, and another law, Gustafson law. Okay, as the problem size increases, the achievable speed up on a parallel system scale linearly with the number of processors. So in Amdahl's law, the problem size is fixed. But in Gustafson law, they are telling if you do the same calculation for the bigger problem, okay, if you scale the problem, then you will get more speed up. Okay, unlike Amdahl's law, which assumes fixed size problem. Okay, Amdahl's law assumes fixed size problem, but here problem will scale. Okay, larger problems utilize more processor efficiently. So Amd also states, irrespective of the number of processors, if you have serial code, your speed up is limited. But here, even if you have serial code, but if you scale the problem size, okay, if you are simulating some 5 atoms, instead of that, if you simulate 100 atoms, so your problem size scales. Okay, so you will get more speed up. If your problem is big, you will get more speed up. Okay. So, okay. Is it visible? Font size is visible, or I will use magnifier for this. Yeah.
Yes, sir, it is visible.
Okay, 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 fine. Okay. So Gustafson law.
A little zoom in maybe.
Okay, I will zoom it. Yeah. Okay. Is it okay now?
Yes, sir, it is okay now.
Okay, okay. Or I will use magnifier. Okay. So let's direct compare Amdahl's law and Gustafson law speed up comparison we are doing now. Okay. So now 95% of the code is parallel. Okay. And 5% is serial. Okay, so how you represent? So one is so 95 means 0.95 is parallel and 0.05 is serial. Okay, number of processor I am going to use 128 cores. Okay, so as per Amdahl's law, speed up is calculated like this. Okay. So speed up formula is 1 by 1 minus p plus p by n. Okay, I think better I will. Yeah. Yeah. So P is equal to 0.95, 1 minus P is 0.05. Okay. So we are substituting this value in the formula, and 128 is the number of cores I am going to use. So approximately I am getting 17.42 times faster. Okay. So if I use single processor and without parallelizing, I will be getting very less speed. But if I use 128 core processor and 95% of my code is parallel, then I will get 17.42 times faster as per Amdahl's law. Okay. Now we will see Amdahl's law does not define whether the problem will scale or not. But here Gustafson law discuss about scaling. Okay. So here Gustafson law formula is n minus alpha n minus 1. Okay, n is number of processors you are going to use. That is 128. Alpha is serial part. Okay, 0.05. So if you just apply 128 minus alpha 0.05 into 128 minus 1. So it become like this. So it is 121.65 times faster. As per Amdahl's law, it is 17 point sometimes only. But here, as per Gustafson law, it is 121.65 times faster. So in HPC, if your problem size is big, that means if your problems can scale, okay, then you will get more advantage according to Gustafson law. So most of the problems, for example, if even your computer may be having thousands of cores, but if your problem size cannot scale, for example, what is scalability? For example, I am doing one work. Okay, I am taking 10 hours to complete the work. Okay, if I deploy two more persons, for example, if 2% do the work, okay, so 10 hours can become 5 hours, but if I deploy 4 hours, it can become 5 hours also, 5 hours or 2 hours, but it cannot go like that because communication bottleneck will be there. Some problem may not scale also. If you give more resources also, it may not scale. So those problem which can scale well, they will get advantage in HPC. Okay. For example, this is one person is doing one job, and for example, if you deploy it 5%, then 5% may talk to each other and they may even worse than one person's performance. That may also happen. So communication bottlenecks also there in HPC. Okay. So this is the comparison. Yeah. So serial portion is 5%. Number of processor used is 128. As per Amdahl's law speed up, it is 17.42x, and Gustafson law speed up is 121.61. So we are in HPC and computation general, we have to see the scalability. Scalability important actually. Any doubt in this? Gustafson law? Okay. Then there is a concept called Dennard scaling. So Dennard, he is a scientist. Robert H. Dennard refers to the key principle from IBM research paper actually. As transistor gets smaller, their power density stays constant. Okay. So for example, in 2020, in the year 2020 and 2025, so chip of size 1 square centimeter, chip of size 1 square centimeter, same. Okay. So in 2020, here in this area, 1000 transistors are packed. In 2025, here it is 2000 transistors packed. Okay, Dennard scaling is the transistor gets smaller, their power density stay constant. That means transistor is getting smaller, but the power density is constant. For example, this takes 2 watt power, And in 2025 also, this also takes 2 watt power. Okay. So how it is possible? Because what is power formula? Power is equal to voltage into current. So power remains constant means voltage and current is reducing. Okay. 2020 the transistor voltage, for example, if it is 10 volt, 2025 it will be 5 volt only, and current also it will be reduced, so that it maintains the same power, but number of transistors increasing. Okay. So voltage and current scale down with size. Switching speed increases. That means that heads, number of heads increases. Power consumption per transistor stay roughly the same. 2 watt, here also 2 watt. Okay. This is called Dinard scaling. Okay, from 1974. Around 2020, this Dinard scaling also broken. Okay. This is also no more valid now. So that's why single core become multiple cores, because we are getting when we are moving to smaller size, atom size, now it is atom size, we are coming to transistors. So it is actually giving quantum behaviors. So why did not scaling broke down? Okay, after 2005 this broke down. Voltage could not keep dropping due to threshold voltage limit. So you cannot keep on reducing the voltage. Leaking current become too high. Okay. Power density begin to increase, leading to overheating. So if it is overheating, then CPU throttling will happen. What is CPU throttling? So there will be a power cap for everything. Okay. So if beyond that power, if it reaches 100 degrees Celsius or something, then the processor will work differently. Okay, that is called throttling. Okay, it automatically it reduces the frequency to safeguard itself. Okay, I can show you on live HPC. I can show you. Sensors command. So this is, so this, it has 16 core plus 16 core, 2 socket. Okay, so this is now running in 42 degrees Celsius. So this is high is 80. After that, one amber indication will come. After 98 degrees Celsius, it will start throttling. It's a CPU throttling means it is running in some heads. Okay. For example, this is running in 2.3 gigahertz. It can go to some level. After that, it will reduce the frequency to reduce the heat. So that is called, if it reduces the frequency, then automatically the number of flops per second reduces, because in flops we have seen already it has number of cores into frequency into number of flops. Okay, so if it reduces the frequency, it reduces the performance also. So that is called throttling, to safeguard it from switching off. That is called throttling. Okay. The result of the end, traditional single core scaling stopped. Okay. Industry moved to multi-core, low power design and new materials. That's why we went for multi-core architecture. Okay. Yeah. So this is simple, power into power is equal to V into I. Same formula we are representing in terms of capacitance, voltage and frequency. Okay. So Dinard scaling relation using K. Okay, it is length. If length increases, voltage decreases, power decreases by square root. Okay. So quadratic power saving with scaling. Okay. So if it scales, well, power will be less, but so that we have to reduce the frequency, voltage and current we cannot reduce beyond certain limit. So we are going for multi-core architecture. Okay. So any doubt? Next we will see HPC architecture, everything. Okay, Amdahl's law and Guptason, no, it is not same. It is different. Amdahl's law will not consider scaling of the application. Guptason law only considers scaling. So it's application scaling. Based on the application scaling, Guptason law. So it's a benchmark we can do, HPL benchmark. Benchmark is based on Guptason only. Benchmark actually we are doing with HPL, high performance LinPack benchmark. LinPack is linear algebra subroutines. There is a default program actually that will be run and it will give some result. Okay, how much teraflop. So it's a basic matrix calculation, row order, column order. So some standard programs so that it requires more computation. So with that we are doing benchmark, and mostly Amdahl's law is old one. Gustafson was a new one. Okay. Yeah, how to justify this comparison? Yeah, we can compare with HPL benchmark. Theoretical calculation you can do with the formula itself. Practical we have to do with HPL benchmark only. No, both are not empirical formulas. Yeah, only HPL is the empirical thing. Okay, this law are extended to quantum computers, or these are, no sir, I think this is only for because quantum totally it's different. I think as of now it is only for HPC only. These laws are only for HPC. Like here we are telling teraflop, petaflop, like that. In quantum computer we are telling quantum volume. So the terminology will be different. In quantum computer we are calling it a quantum volume, because we cannot guess. Okay, if the number of qubits is more, we cannot say that quantum computer is powerful, because it depends on many factors. So that all factor put together they are giving some number called quantum volume. Okay. How do you determine what percentage of code is parallelized, since a lot of code could be abstracted when you use API? In HPC we have to parallelize it, sir. Using MPI OpenMP program we have to parallelize it. Then mostly it is loops. So mostly through OpenMP multi-threading program. So we have to parallelize it, and then there are a lot of tools actually. We have to write parallel program, and we have to convert serial to parallel, because old legacy codes are still in serial only. So a lot of people are doing conversion from serial to parallel. Mostly it's loops. Loops will be parallelized with OpenMP and MPI program. Scaling is represented as n only. If you change the if you change the n, you will see the difference in the formula. Now we checked with 128 core. If you do 64, the scaling will drastically reduce. If you further use instead of 128, if you use 256, the scaling will be more. But the same level of scaling will not happen if you use this formula. Yeah, Amdahl's law. There is no separate scaling function. That n is the scaling. N only represents scaling part here. Yeah. Okay. Okay. So next we will see HPC architecture. HPC is nothing but it's a normal server only. Okay. Normal server only. but multiple server connected with special switch and connected to the special storage. Storage and network is special. Okay, so three components: compute, network, storage. Okay. Excuse me. HPC cluster architecture consists of multiple compute server network together to form a cluster that offer more performance than single computer. Okay, so it's a normal commodity servers only, high-end servers with a number of cores more, memory more. Okay, normal servers only. It's all interconnected with special switch that is called InfiniBand switch. Okay, then storage is special, parallel file system. Like many of you know Hadoop. Hadoop is a distributed file system. Here we use parallel file system called Lustre, GPFS, BGFS, like that. Many parallel file systems are there. Mostly we are using Lustre file system. Okay. Okay. So I will show you. So why we are using special network? See, okay. Why we are using special network? Why not Ethernet? Ethernet actually can give more bandwidth also, no issue. But Ethernet actually follows that ISO OSI layer 7-layer architecture. So every layer, application layer, presentation layer, session layer, transport layer, network layer, data link layer, physical layer, all this OSI layer, it will follow. And everywhere encapsulation will be there. And again in reverse, it will be going for decapsulation. Okay. So the latency of the Ethernet switch will be very high. Since from some part of the program will be executed in one server, some part will be executed in this, both server has to do message communication. Okay, if the latency is more, then the message communication also will be delayed. So the processor idle time will be more. So we need, so network should not be a bottleneck. So we use special kind of network called InfiniBand switch. So here this all this encapsulation, decapsulation is avoided. It works in the concept called RDMA. RDMA. Okay, it works in the concept called RDMA. RDMA. I think most of the computer science people, they know DMA, direct memory access concept. This is RDMA is remote direct memory access concept. Okay, so that's why here latency is very less. That's why we are using InfiniBand switch. And storage, since this server also computing the same problem, this also same problem, this also same problem, but so they have to write the same, they have to read from the same file, they have to write to the same output file. So parallel IO and parallel read and parallel write is needed. Okay. Parallel read and write. That is not possible with normal file system. In distributed file system, parallel read is possible. That is concurrent read is possible, but concurrent write is not possible in distributed file system like Hadoop. But here in parallel file system, concurrent read and concurrent write is possible. That's why we are using this kind of storage here. Okay. So compute is normal compute only. Compute is normal server, low latency network. This is parallel read and write. So here these two things are different. Network and storage is different for HPC. Okay. Otherwise it is same. Okay. So core components of HPC is user, then network, then master node, then scheduler. Actually many people will be using HPC, so we need a scheduler. Okay, why scheduler is required? So if you have a common resource and if you want to effectively use those common resource, then scheduler is needed. So why we are having timetable? So because classrooms are the resource, our faculties are the resource. So to use the resource effectively, we need some kind of scheduler. Timetable is one type of scheduler only. So here also in HPC we need scheduler, and then nodes, storage. These are the components of HPC. Okay. So just I will log into our HPC and I will show you so that you will get some knowledge about HPC. So this is one HPC. Okay, I will just show you another website. So this is top500.org. This is a global list. Top sc.cdac.b, cdacb.in. This is India list actually. Indian list also published every 6 months. So in January 2025, CDAC Pune, Airavat, this is the number one. And here you see in the global list, we are in 136, same mission. Okay, 8.5, 13.17. 8.5, it is mentioned in terms of teraflop, just you can divide by 1000. So it become 8.5 and 13.17, same mission. Okay, so in India, it is number one. In the global list, it is in the 136th position. So here, I'm just showing one cluster. Ours also very now it's almost 7 years old cluster. Maybe we will be in some 60th position or something. Okay, no issue. Let it be. Okay, so this is a cluster with 100 nodes. Okay, so N1 to 60. This is 60 nodes. Okay, 66. So these are allocated means these are all now running jobs. Idle means this node is idle now. Mixed means, for example, if it has 40 core, not all 40 is used, some 30 is used and 10 will be remaining. So it is called mixed state. So these are all multiple queues. So these are all multiple nodes available. Okay. So here, so each node has 32 core, and this is the core, this is the frequency, everything. Okay. So I can go to some, these are new nodes actually, or LS CPU. So these are 40 cores, 0 to 39 cores. So 40 core, I can just show less or okay. Or we can use cat proc CPU info. Most of the HPC will be running in Linux only. 99% of the HPC will be running in Linux only. I have never seen Windows HPC. So processor 0, processor 1, 2, 3, 4. So this is one machine, okay, up to 40. So this is one machine, and this many, so 97 machines are there, 97 servers are there. They are all connected with this switch, okay, IB state. This switch speed is 100 Gbps, okay. This speed is 100 Gbps. Latency is very, very less in terms of nanosecond, okay. And Ethernet switch latency will be in terms of milliseconds. Okay. And here, this is the storage, which is a parallel file system. This storage is mounted in all the nodes. So we have 205 TB of storage. Out of that, this much is used, and this much is still available for use. Okay, so here this many nodes are there. Okay, what people are doing with this cluster? SQ command, it will show the jobs. Okay, these jobs are running now. So these jobs PD state, these are pending state. Okay, this many jobs are pending. These many jobs are pending, waiting for the resource. This is a scheduler. Okay, so this still, this many jobs are there. Okay, these are the running jobs. Okay, or running jobs. So this many jobs are running. So this job is running in 93 node, or the 93 is node number. It is running in one node. Okay, this is running in 5 nodes. 5 node means each node has 40 core. That means 5 into 40, 200 core. This job is running in 200 core. Okay, so this is also 200 core. This is running in 64 core. Sorry, 40 core. So this many jobs are running. I will just show you what they are running. For example, I will take this job ID. To show job. Okay, so this is about the job information. This is to assign to whom priority, what is the priority, when did he submit the job, when it is eligible for some execution, when it is started execution, when it will schedule. So all this information, node, which node. So total is 200 CPU it is running. Okay, so all these things. Command, what command he used to submit this job? He used this script to submit this job. Okay, just opening that script. So this is the job script. Through job script only he is submitting the job. Okay, so he is just mentioning these are syntax. Okay, slum, this is one scheduler called slum. So job name, what is the job name? So which queue it has to submit? Number of nodes, 5 nodes. Number of cores per node, 40. Output file where to write. So he's just writing MPI program. So his own program he's writing. /a. His own program is just running. Okay. Okay. Any doubt? Okay. Okay. PFS products, parallel file system, Luster. So Luster, GPFS, BGFS. These are some of the parallel file systems. Which Linux is this? Okay, this is actually 9 years old cluster. We are using CentOS only. etc Red Hat release. It is CentOS 7.8. Okay, uname-a. Okay. Yeah. It's a kernel. Uname-a will give kernel only. Okay. So cat etc Red Hat release will tell which OS. Okay. Yes, actually this cluster is very old actually, but new clusters we are using Rocky Linux. Okay, I will show you another server. Here Rocky 9.4 we are using. This is 9 years old cluster actually. That's why we are not upgrading it. It is almost end of life. So for new servers, we are using Rocky Linux because CentOS is no more supported. And other things, Ubuntu also some people are doing, but we are happy with Rocky Linux and sometimes Alma Linux. But mostly we use Rocky Linux 9.4 only for new clusters. Actually, Debian sometimes it breaks. Actually, its stability is not there that much. So that's why we are going for Rocky. Actually, stability is more because for HPC we cannot frequently reinstall because there are multiple softwares. Okay, multiple softwares installed. For example, I will show you what are the softwares available in our HPC. So these many softwares we have installed. Again, redoing is actually painful job. That's why we are not. And we can. Okay, so if you want a latest version of C compilers, GCC compiler, whatever it is, we can install through module. Okay, no issue. For example, now which GCC hyphen version. So it is default is 4 point something, 4.7 maybe. This is 4.8.5, but new softwares may not support this compiler. So in that time, we installed everything as a module. Okay. For example, I want latest compiler means I can load this. I have installed already the compiler GCC 9.2. Okay. So now if you just give the command, so no need to reinstall the cluster when OS or everything changing. No need to install it. We can install everything as a module and we can upgrade it. Okay, multiple version of the same software can be there. For example, GCC 4.7 is there or 4.8 is there. Okay, so I've installed 7.5, 11.3. All these things is possible without disturbing the base OS. Multiple versions can be installed using model environment, so that no need to reinstall again, because everything is for reinstalling. It will take long time actually. Okay, it's a Monte Carlo. Yeah, Monte Carlo simulation. All type of simulations are there. Can other academic institute access this cluster? With permission, you can access. Yeah, but mostly here actually too much users. I have seen. I have shown you. No? So this many jobs are already waiting for. It's completely full. So this many jobs already, they will be fighting for the cluster. Actually, this many jobs are already in pending state. But CDAC can give. Here, actually, this is one department cluster only. We have multiple clusters. So too much jobs are waiting actually. Here, almost 200 plus users are there. Faculty itself to 25. PA users, 200 faculty, 200 students. So it's completely busy. This cluster is completely busy. Build in spec. So current GCC is 14.2. I am a Debian testing. Okay. Yeah, GCC we can install. Even 14.2 also we can install in this clusters model. If requirement comes, we can install it. That is not an issue. So mainly for OS upgradation, GCC and many packages are needed. So we can reinstall it. Without disturbing the OS also, we can reinstall it. We can have multiple versions of GCC also. That is not an issue. Okay. Okay. So we will go ahead. Okay, so now we will come to GPU. So we are having less GPU as of now. So, but we have GPU servers. For example, this is GPU server with this is another server with a GPU. NVIDIA SMI if you give. So it's a A30 card. Okay, A30 with 24 GB GPU RAM. Okay. Okay. So in HPC, why we need graphics card? So GPU actually good for highly parallel jobs. So CPU is designed to excel at executing a sequence of operation called a threads as fast as possible and can execute a few tens of threads in parallel. But always CPU is faster, but GPU can do parallel task. Okay. So here difference between GPU and GPUs, this green color things are the ALU, arithmetic and logic units. Okay. So here more ALUs. So here 1, 2, 3, 4 cores only. Each has L1 cache, control unit, L2 cache, L3 cache, and DRAM. Okay, this is a CPU architecture. So CPU is called multi-core and GPU is called many-core. So these green things are ALU. This yellow things are control, and this blue is cache. Okay, so individual cache is also there, shared cache also there, and DRAM. Here DRAM also fast. Okay, so more ALU, that means this is completely designed for parallel. Designed for parallel. Okay. Okay. What is GP GPU? GP is general purpose. Actually, GPU is only for graphics. Okay. GPU is for graphics. So GPU is even same graphics card. We not same graphics card. Some special again some more units are added to this same GPU, so that it can be used for general purpose. General purpose GPU. Okay. So we are using general purpose GPU in HPC because GPU it is designed for parallelism. So more massive parallelism, high throughput. Actually, memory bandwidth is more in GPU than CPU memory. GPU memory I actually DDR6 has come, but still CPU in DDR5 only, and high bandwidth memory is there. So high throughput is possible with the GPU memory. Okay, and energy efficient number of flops per watt, that is more in GPU, and teraflop advantage we have. So that already I showed you teraflop advantage. For example, teraflop advantage here we have seen. So see, here it is 2.5 teraflop, but here number of cores is more, so it is 30 teraflops. So teraflop advantage is there in GPU. Okay. Memory bandwidth is more in GPU memory, ecosystem and tools. So CUDA, NVIDIA, actually everything is given by NVIDIA. So tools, everything is there available. Addressing architecture limit. So Moore's law, Dinner scaling. So all these things actually there is a limitation in the CPU, but GPU actually solves those limitations. Okay, what is the architectural difference? So few powerful complex cores in CPU. Here's not that much powerful, but hundreds of thousands simple cores. Sequential task, the CPU is good for sequential tasks, GPU is good for parallel tasks. Architecture here, large cache, branch prediction, control units. Here, many ALUs, that green part. Many ALUs are there. Okay. And single instruction, multiple data as per Flynn's taxonomy. Single instruction, multiple thread is also here. It's a vector processing. Okay. So strong single thread performance, but fast data parallelism. Mainly it is good for matrix solving. So OS, logically heavy apps, control flow. But here GPU cannot work without CPU. For initializing GPU, we need CPU. So simply with GPU, we cannot perform any task. So initializing everything will be done by CPU only. Do not have, so there are two types of GPU. For example, in your laptop, it will be integrated GPU or some dedicated GPU cards. So what is the difference between integrated GPU cards and dedicated GPU cards? Integrated GPU card do not have dedicated memory. It uses the same CPU RAM only. But dedicated GPU has dedicated RAM in that. Okay, so that you can do a lot of operations in that GPU. But this one, integrated GPU is only good for graphics application. Okay, CPU versus GPU. So clock speed, CPU will be high, GPU will be low, few cores, many cores. So main function handles all type of main functions, but here only parallel. So processing is a serial instruction processing. This is designed for parallel. So general purpose computing application, GPU is high performance computing application. So operation focus, low latency, GPU is high latency. So here GPU is not good. Latency low, it should be low. Latency should be low. So MPI program, everything, CPU, it will perform very well. Okay, matrix things, GPU will perform very well. So if your application depends on more MPI, then CPU will give more performance. Okay. If it is based on matrix, then GPU will give more performance. Interact with more component like RAM, ROM. So CPU is complete. GPU interact only with RAM and display. Execute numeral tasks, so execute limited tasks. GPU only limited tasks can be executed, but it is highly parallel and it's a special processor. Okay. No API limitation. Any API can be integrated, but here limited APIs. Slower but multiple threads. No interrupt context scheduling. Okay. Okay. So host is called CPU, device is called GPU. Okay. GPU is called device. Okay. Okay, so this is about this my A30 GPU anatomy. So here it is Amber architecture. Okay, here SM is symmetric multiprocessing. Okay, streaming multiprocessing or streaming multiprocessor. Okay, streaming multiprocessor. So here 56 streaming multiprocessors are there. In each streaming multiprocessor, 128 CUDA cores are there. So 128 into 56, 7168 total cores are there. And this is CUDA core. There is other type of core, that is tensor core, 222 total tensor core, 4 per SM. That means total 56 SM, 4 per SM, 56 into 4, 224. Okay. Total memory is 24 GB high bandwidth memory, 2. Okay. Memory bandwidth 933 gigabytes per second. PCI interface, or one more type interface is also there, NVLink. Okay. Peak performance is 10.3 teraflop. Peak tensor performance is 330 teraflop with sparse matrix calculation. Okay. Here, so it takes 24 GB. Okay, it is mentioned in MIB. If you convert, you will get 24 GB. Okay, so this is the Sakura version driver, and these things are there. Right now, yeah, nobody is using R. Okay. Okay, this is the NVIDIA GPU architecture. Okay. So NVIDIA GPU will be like this, look like this. GPC, graphics processing cluster. This single unit is called GPC, graphics class. One, two, three, four, total 8 GPCs are there. GPC is graphic processing cluster. GPC. Graphics processing cluster. So 8 GPCs are there. Then under each GPC, here actually if you zoom, okay, so memory controller, high bandwidth memory are connected to the GPU through high bandwidth through memory controllers. Okay, each GPC, graphics processing cluster, has multiple TPC. Okay, thread processing cluster. Then each thread processing cluster has SM, streaming multiprocessors. Okay, and this side actually memory is connected with controllers. Okay, and here that NVLink interface, PCI interface for connecting with the server, it is there. Okay. Okay. High speed hub. Okay. So graphics processing cluster, this is called graphics processing cluster. Each graphics processing cluster has TPC and SM. Okay. So texture processing cluster. Okay. So TPC has 2 SM. Each TPC has 2 SM. Okay. So TPC is inside. So graphics processing cluster, texture processing cluster, 2 SM multiprocessing with per TPC and 4 process block per SM. Okay. So this is process block. Here, if you see, here integer units, 32-bit integer it will process. How many units are there? 8 plus 8, 16 units are there. floating point, 32 floating point operation, this many units are there, it will do. And 64 bit, that is double precision. So mostly for HPC, we will use double precision only. For machine learning, you can use 32, or even it can be reduced to 16 also. If more approximation is needed, you don't need high precision. So these many units are there. So 4 process block per SM. So each SM has 4 process blocks, 16 floating point 32 per block. Okay. So here 16 is there. 8, one row, one column is 8, and here 8. Each has 16. So 16 into 4, 64. 64 per SM. Okay. So like that it is mentioned here. Okay. Okay, so again it is process block detailed. Okay, and then SFU, special function units are there. So apart from this matrix, trigonometry function can be done by SFU, exponential, reciprocal. So for a tensor operation can be done by tensor core. So for every operation, special cores are there, hardware is there. So okay, okay, so okay, we have to use CUDA-Q to simulate quantum computer, or if any QPU integration in the HPC, we have to use CUDA-Q. Okay, so there are CPU, GPU, QPU. Okay, GPU, QPU, central processing unit, graphic processing unit, QPU. So now we are using this both in HPC. In future, we will be integrating QPU also in HPC. Okay, so in that for CUDA-Q, will be supported with some graphics card only, not older graphics card it is not supporting. So NVIDIA actually gives number for each GPU, that is called compute capability. Okay, so CUDA-Q, to run CUDA-Q, at least you need compute capability of 7 plus. So more than 7. So if you are trying to run, or if you are interested in purchasing GPU, then you should consider this. Okay, so there are a lot of architecture, Kepler architecture, that compute capability is 3 point only, 3.x. So this is major number and minor number, depends on the capability. This number is provided by NVIDIA only, we no need to calculate. Okay, NVIDIA GPU compute capability is a versatile system used by NVIDIA to indicate features and capability of their CUDA enabled GPU. It is denoted as a pair of numbers, major dot minor, 7.5, 8.6, 9.6, etc. Okay, so we have a lot of machines, Kepler architecture, Maxwell architecture, Pascal, many different type of GPU cards are there. So your CUDA-Q will run after 7. Okay, so while purchasing you have to be very careful, otherwise the CUDA program will not run. Okay, better to go with 8 and above because they are changing frequently. Okay, okay, any doubt? Why matrix multiplication or linear algebra is more suitable for GPU? It is a high precision, not a priority for linear algebra. Even if I much more. No, here actually precision does not comes actually. GPU by default it is good for matrix. Okay, because so many ALUs are there. So it is good for matrix multiplication, matrix addition, everything. Okay, that's why linear algebra definitely it is converted into matrix. So GPU is perfect for matrix calculation. That's why GPU is used. What is 7 plus capability? When to decide? Okay, when purchase. Actually, this 7 plus is a number actually. For each GPU, if you search, they will give the compute capability. That is a number given by NVIDIA itself. So CUDA-Q will support after 7 only. So that functionality is in the old card, that functionality is not there. That's why you have to see while purchasing, you have to see whether that NVIDIA GPU has compute capability of more than 7 or not. Now 9 everything is coming, so you have to see the compute capability before purchasing. Otherwise you cannot run CUDA-Q program in that GPU. Actually, this is a number given by NVIDIA itself, so we don't want to do any calculation here. So they will tell, because based on the, so here you see every GPU they are increasing some features. So in this GPU they introduced dynamic parallelism feature. In this GPU they've identified unified memory basis. Okay, then NVLink, then Tensor Core, then RT, ray tracing. Okay, that is for graphics application. That is like your shadow effect. Those cores are added. RT cores are added in that. Earlier they used to do with some other core only, but here, for example, if you have I think most of the people know RISC versus CISC architecture. RISC is reduced instruction set computer, CISC is complex instruction set computer. Okay, CISC versus RISC. CISC is complex instruction set computer, this is reduced instruction set computer. So for example, in RISC, if you have only add and subtract instructions, how will you do multiplication? How to do multiplication, division, etc. So repeated addition is multiplication. Okay, a repeated addition. Like division can be done with repeated subtraction. Repeated subtraction. So when the instruction is not available in the processor, instruction set architecture, ISA, then you have to use that simple instruction and you have to write a program and you have to do. Okay, indirectly you have to do that calculation. Okay, but in complex instructions in computer, you'll be having addition, subtraction, multiplication, some other advanced instructions also. So that here writing program will be easy. In CISC, writing program will be easy. Okay, but in RISC, program will be difficult. But processor is complex. Okay, if processor is complex, program will become easy. Programmer's headache is less. If processor is less complex, then program, the complexity moves to the programming. Okay, so like that RT core, ray tracing core, for shadow effect and all, you can just use this core and directly perform the operation. Okay, so CUDA execution model is thread, block, grid. Okay, so in the base it is thread only, then the group of thread is called blocks, then the group of blocks is called grid. Okay, this is a big topic actually. For GPU CUDA programming they will be learning. So one dimensional, two dimensional, three dimensional, like that. Because if you want to point some thread to do some operation and another thread you are pointing to do another operation, then you have to find out the thread number. Based on the thread number only you can assign. Okay, number 32 you do this number, because there are number of threads. Okay, each thread can be given a single operation, so that you have to point to the thread with the thread number, thread block ID, numbers. Okay, so in this block, in this grid, in this grid, in this block, in this thread, so this thread you do. Okay, for example, I have 10 grids and each grid has 10 blocks and each block has 10 threads. Okay, so totally how much I have, how much threads I have? So I have 10 grids, 10 blocks, and in each block 10 threads. How much it will be? It is 10 into 10 into 10. So total 1000 threads I have. Okay, I can assign each work, I can assign single work, separate work to each threads, so that highly parallel it becomes highly parallel. But how to mention that, okay, which thread to do which operation? So you have to have thread id, block id. So through thread id, block id only I can mention this. Okay, for example, so this is, okay, this is one or something. Okay, for example, I want to mention, so how I will naming convention for this all 1000 threads. So for, second grid, third block, third thread. So like that, some naming convention should be there to point to that thread. Then only that thread will do the operation. And similarly, with this number thread id, you can assign the task to each threads. Okay, so this thread id, block id, grid id calculation, some formulas are there. Okay, that can learn. Okay, this is how GPU highly parallel. Okay, okay, CUDA parallel program. So thread versus block versus grid. Smaller unit of thread is smaller unit of execution and individual calculation. A group of thread that can communicate and synchronize, running on an streaming multiprocessor (SM). Grid is a collection of blocks, the entire kernel execution. So what is kernel? What is device? In C++ function executing by many thread on the GPU, the parallel code is called kernel. Device, GPU itself is called device. Okay, so device is GPU, host is CPU. Okay, three terms you have to understand. Host, device, kernel. Host is CPU, because without CPU, GPU cannot work. So CPU is needed for initializing the device, everything. Okay, device is GPU, and kernel is the code which runs in GPU. Code which run on GPU. Okay. Okay, so what are the challenges of HPC? So I'm just not listing this. There are a lot of fields. Okay, so without HPC, science is not there. Physics, you can just prefix the word computation. Chemistry, you can prefix the word computation. Computational chemistry, computational biology, computation economics. So everything need HPC. Okay. So challenges in HPC. What are the challenges in HPC? Present HPC. Flop increases faster than memory access speed. So CPU performance is increasing, but memory performance is still bottleneck. Okay. Then IO is still bottleneck. Okay. Increased clock speed and density lead to higher power consumption. So power consumption is more. Now data center power is more actually. Okay. So CPU is getting heated up because so many cores are packed in very little area. So the heat, it may melt, even CPU may melt actually, that much heat is generated. Cooling and energy loss is a big challenge. So memory bandwidth is a big challenge. That's why now DDR4, DDR5, all this memory bandwidth increasing. Okay. Need for energy efficient high performance computing. These are the challenges. And then communication bottleneck. So as I told, the latency should be very less, because both the servers are doing, for example, I have a big problem. That problem is divided into different chunks, and each chunk is given to different server, and all the server has to communicate. Okay, that communication, if it become latency more, then the entire CPU idle time will be more. So communication should not be latency, and communication is a big bottleneck. Okay, how classical HPC powers quantum computer? So we can simulate with in HPC we can simulate quantum computing also. Okay, why hybrid? So till we are in the noisy intermediate levels quantum only, full fault tolerant, we don't know when it will come, maybe 10-15 years. Okay, so we have to use the existing infrastructure to understand and learn quantum computing. Okay, so just okay, open source platform. CUDA-Q is NVIDIA's quantum programming, like Qiskit by IBM. CUDA-Q actually uses GPU for quantum programming. Open source platform optimized for NVIDIA GPU. So it can, it's not only simulator. In future, if QPU comes, you can program QPU also, quantum processing unit also. You can program with CUDA-Q. Okay, seamless integration, Python and C++ both. It gives the framework. So quantum kernel you can execute, quantum kernel and quantum circuit you can execute in the GPU itself. Unified programming model. So you can do CPU, QPU, GPU all. So one program. So now Intel one API like that, hybrid programming. So one program that can that is called XPU now. Now the term is called XPU. Hybrid programming. XPU. X can be anything. X can be C, G, or Q. CPU, GPU, QPU. So XPU, yeah, heterogeneous programming. That is called heterogeneous programming. Now the trend is like that. Heterogeneous programming. Okay, so installing CUDA-Q is very simple. Okay, if you have Python environment, Anaconda Python environment will be very good supportive. So just you have to create, actually this command, only this command is enough. But if you have Anaconda environment, this command itself enough. Okay, and you need to have CUDA and you need to have GPU. Right now, CUDA is only supported on Linux operating system. It can be run on Windows also with Windows subsystem for Linux. Okay, like Ubuntu. So Windows subsystem for Linux. In Windows also you can install this Ubuntu and you can run. So it is only supported Linux operating system. Okay. Fundamental building block of CUDA-Q is so this is a kernel, your quantum program. Okay. We will just go to the program actually. Okay, CUDA-Q kernel. Okay. Okay, we will just go to the program and we'll see. Okay. Okay. So we will create a bell state now. This is a bell state. Can create circuit like this. Okay. This is the CUDA-Q program, Python program. So we are importing CUDA-Q. Then after this line at CUDA-Q.kernel. Okay. Then this after this line, it's executed by QPU. These lines will be executed by QPU or GPU simulator. Okay. So we are defining the kernel. Kernel name is bell state circuit. Then we are creating two qubits. Qubits is equal to CUDA-Q.Q vector 2. That means we are creating two qubits. And we are applying Hadamard gate on qubit 0. Okay. And we are applying CNOT gate on qubit 0 and qubit 1. Qubit 0 is the control qubit and qubit 1 is the target qubit. Then MZ is a measurement. We are measuring this qubit in Z basis. M is at measure on Z basis. This 2 qubits we are measuring. Okay. Then for visualizing, okay, I'm just running this code. Okay. Okay. So I have to first load these things. Good. Okay. Environment is now activated. Now, so 1 qubit, 2 qubits are created, and first qubit is assigned Hadamard gate. So you will get superposition state. Then we are applying C0 gate. So this is the Bell state preparation. So here this is the measurement. Okay. Here this is the measurement. 2 qubits, and the number of shards is 1000. 489 times we are getting 0, and 511 times we are getting 1. Okay. So in 2 qubit we should get in 2 qubits we should get 00, 01, 10, 11. So 4 states we should get, but in fully entangled things we should get only 2 state, 00 and 11. Okay, 11 and 00. So we are getting 00 and 11. Okay. Any doubt? Sir, RC is a ray tracing course, sir. Ray tracing. Ray tracing is like shadow effect. Ray tracing core. Okay, it's a shadow effect. Okay, for graphics purpose. The multiplication by repeated add will take by code generated by compiler, I suppose. Yeah, but it will be slow. No, it will be slow. Or in that logic should be in the program. But now GPU, actually now we are using x86 processors. Okay, in future it will be now many people have already started using RISC processor, ARM processor, advanced RISC machine. So still libraries are not there. Okay, so still they are in development. So in Japan one machine is erected, and still we are not using a RISC processor. But in future it will be RISC only. Now we are using x86. That is CISC processor, complex instruction computer. In future, the HPC will move to RISC, reduced instructions in computer. So that now CISC manufacturer is only Intel and AMD. But if you go for ARM processor, there are a lot of people are manufacturing. Okay, so even our CDAC and IIT Chennai, Viga processor. So we can use our processor also for computation. So that will be the future. Okay. Yeah. So which part of this that is defined by at kernel? So here we are mentioning na, at CUDA kernel. After that, this part will be executed by QPU. Before that, it will be GPU. Sorry, GPU or CPU. Okay. Here it will be quantum part. At CUDA.kernel only defines that. Is there a way as a quantum can have access to this for CUDA Q experiment? Actually, this Cube and other platform, they are charging actually for because they are giving 2 virtual CPUs only free, but for GPU and all they are charging. In yeah, they are charging actually per hour basis. They are charging. Yeah, But even low-end graphics card now, RTX 2080, RTX 2080 also, they are having more than seven actually. This may be 2-3 lakhs, but none of the cloud providers, they are not giving. I don't know, I checked some 3-4 things. They are not giving anything free of cost. Those they are giving only virtual CPUs. Two CPUs only they are giving, no GPU they are not giving. Okay, so we will run another program. Okay, uh, so Python Hadamard. Okay, this is just creating Hadamard gate. Hadamard is, so 0 is in point 0, so 1000 times we are running. Hadamard code I will just show you. So import CUDA at CUDA.kernel. So it tells that, okay, hereafter this starts, and indentation is important. After defining kernel, you have to give tab, otherwise you will get error. In Python, same Python. So one qubit is initialized, and for that qubit Hadamard gate is applied and it is measured, and result we are getting and we are printing. Okay, so okay, we'll just show one last program. Okay, so CUDA-Q is something. So CUDA-Q kernel is the fundamental building block of defining quantum computation. It is essential to function that quantum instruction and is designed to be executed on quantum processing unit. So either it can be after CUDA kernel, it can be in the QPU, or it can be simulated QPU. Simulated QPU is our GPU with compute capability more than 7. Okay, compute capability. You can simulate. So H, X, R, Y, these are all the gates measurements we can use. Okay. So what is, okay. Kernel is a function that measures similarity between two classical. So every quantum circuit is a kernel, but not every kernel is a quantum circuit. Okay. So, okay, I will run one Jupyter notebook. Circuit has three parts. Okay, first you have to encode information into quantum state by initializing qubits. First we have to initialize the qubit, then we have to apply the quantum gates for manipulation, then we have to measure it, extract information from the quantum state by measuring. Okay, so initializing, manipulating with quantum gates, and measurement. Okay, so we are just creating bit flip experiment. So by default it is 0. When you apply Pauli X gate, the bit will flip. Okay, so import CUDA. These things are needed for visualizing. Okay, Python widgets, these things are needed to visualize it. So actual quantum program starts after CUDA-Q.kernel, and we are defining a kernel called bit flip. Then we are creating one qubit. Okay, then we are visualizing it by CUDA-Q.show function. So now it is in the default 0. Okay, qubit is initialized to 0. Now we will apply Pauli X gate so that it will be pointing to 1. Okay. So now we are doing bit flip. One qubit we are initializing, and then we are applying X gate on qubit 0, first qubit. There is only one qubit here. So after initializing, it points to 1. Okay, 0 become 1. So bit flip. So this is just applying. Okay, this last 2 slides are there. Okay, so these are all some of the syntaxes, qlock, kernel, these things. Okay, Adamar gate we created. Okay, this I will discuss. GHZ, okay, state. GHZ, okay, this is a scientist name, Greenberg, Horan, Zellinger state is a fundamental and highly significant type of entangled qubits. In Bell state, we are creating 2 qubits entanglement only, but in this state, we can create more than 2. Sometimes 3 or more qubits, unlike the Bell state, which involves only 2. Okay, so here more qubits can be entangled. So okay, here more qubits can be entangled. I will just go to the, if n qubits is a superposition of all qubit being 0 state and all qubit being 1 state with equal probability. Okay, so I will just explain this. I will come out of this Python. Okay, so Python GHZ. Okay, so by default it creates 3 qubits. Okay, so 3 qubits, since it is fully entangled, 3 qubits, what are the states? 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 1 1 1. So 8 states should be there, but if it is fully entangled, you will get these 2 states only, 0 0 0 1 1 1. Here you are getting. Okay, so for example, okay, I am just creating now 4, okay, 5 qubits I am creating now. Entanglement with 5 qubits I am creating. Okay, you can see only 5 zeros and 5 ones are there. Okay, 5 zeros and 5 ones are there. Now I am increasing the qubits. I am increasing to 10 qubits created. Okay, and entanglement created. 20, it's created. 30, created. 31, it's created. Now 32, it shows error. Okay, 32, it shows error. Running on target NVIDIA, it is running on the GPU, sampling the circuit, running error, required size is too big. Okay, why it is running up to 31 and it is not running 32? Okay, we'll just explain this. I'll provide the slides. Okay. So, okay, so curse of dimensionality in quantum simulation. The runtime error required size is too big when you jump from 31 to 32 qubits is not an error in your code, but the fundamental limitation of the classical quantum simulators, including the powerful GPU accelerator, one like CUDA-Q, NVIDIA Target. Okay. Simulating of n qubit requires 2 power n complex numbers. Okay. So each complex number, for example, if it is floating point 64, then each complex number requires 16 bytes. Okay, so 2 power 16 is, sorry, a few 2 power n. Okay, so in CUDA-Q normally it is floating point 32. That means 1 qubit requires 8 bytes. So 2 power 32 into 8 byte is equal to 16 byte. 31 is 16 kilo GB. Okay, 32 it becomes 32 GB. But my GPU A30 has only 24 GB. That's why after 32 it is creating error. A30 has 24 GB only. So I am able to execute up to 31 qubits. I can create 31 qubits entanglement. But when I try for 32, it is telling memory limit. There is no memory for you. Okay. Understood? Okay. Yeah. Thank you. Any questions? 8 states up to 32. Okay. So I'm done with. So any questions?
There doesn't seem to be any questions, sir, from the
Okay.
participant side.
Okay.
Okay, someone asked.
No, no, no. Quantum computer is not restricted to 31 qubits. It depends on your GPU RAM. See, my GPU has 24 GB only. For example, if you use A100 or any different high level card, then your memory is more, so you can execute that much. That depends on the RAM only. See, you need to mention 8 bytes. Okay, so this is the calculation. If your GPU has 32 GB, then you can
Hmm.
execute 32 also. Next will be 64. So even it is problem is exponential. So even with a high end 80 GB, I think some high end card has 80 GB. Maybe they can simulate 33, 34 qubits only.
Yes, sir. NVIDIA just released in 2025 RTX 6000 Pro. It has,
Ah,
I think, about 90 GBs.
yeah, 90 GB. No? So maximum another one more qubits they can do. Because problem
Hmm.
is here actually that is why we are going for quantum, because we have limitations.
Yes.
Because problem is exponential and the resource also exponentially growing. That is the thing, because now, for example, I am simulating with my HPC 100 atoms. For 101 atom I need double the size of the HPC.
Hmm.
102nd I need again double the size of that previous one. So problem size is scaling and the resource also scaling, but in quantum computing one more qubit is only needed.
Hmm.
That is a now drawback, because we cannot able to simulate larger problems. Because for example, I have bigger HPC. If I want to add one more atom, then the problem size become too big, and power, cooling, everything has become. That's why we are going to quantum. Future will be quantum, because most of the problems still not solved using the HPC also. What is the status of GPU process being developed at um, GPU? I don't know, but the CPU Vega processor, RISC-based processor they are developing. But it is GPU. I don't know what is the status. But they are developing that ARM-based only. But still, we are using x86 only mostly. It will take because libraries has to be developed. It's not only hardware. Library has to be developed, and the application software has to use those libraries. So everything should be in the chain.
Okay, sir. I think we should end this particular session at this point. Thank you for taking time out of your busy schedule and informing the participants uh, of very interesting implementations of quantum computing. Thank you, sir.
Thank you, sir. Thank you very much. Yeah, thank you. Shall I disconnect, sir?
Yes, sir.
Yeah,
You can.
yeah.
Thank
Thank you,
you.
thank you.